Okay, so let's talk about similarity. Definitions and examples of similarity. All right, so we have looked at this situation with two matrices, H and H hat. And these two matrices are matrix equivalent if they are non-singular matrices P and Q such that H hat equals PHQ. We also showed, of course, that if H hat is similar to H, then H is similar to H hat. That was one of the exercises. So we can draw this diagram to illustrate this relationship. If H represents a linear map from V to W, where V is represented with respect to basis B, and W is represented with respect to basis D, we know that if we have a linear map from two such vector spaces, it's represented by a matrix with respect to these two bases. Now, we can also consider the same vector space with respect to a different basis. So we're identifying this vector space here and here. We're simply expressing the vectors in the vector space with respect to a different basis. And similarly, we can express the vectors in W with respect to a different basis. And we saw that the same linear map will be associated with a different matrix if we consider different bases here. Okay, so that's the picture. Now let's consider a special case where, in fact, we have the vector space V in the domain is the same as the vector space W in the range. So we, instead of having V and W here, we have V and V. And also, we consider the case where the range basis is equal to the domain basis. So you can see that the difference between this diagram and this diagram, first of all, the W's have become V's. And second of all, the basis on this side is equal to the basis on this side. So we're considering two different bases of V, the basis B, and considering the linear map, or linear transformation rather, because it is the same vector space, linear transformation T, on the vector space V. Now if we consider this linear transformation in terms of a particular basis B, we'll get a particular matrix T, capital T, that represents that linear transformation. On the other hand, if we consider the same linear transformation with respect to a different basis D, then we'll get a different matrix to represent it. Okay? So let's unpack this equation here. Rep dd of t, that's this matrix T hat, is equal to rep bd of id times rep bb of t times rep bd of id inverse. So let's follow this through. Why is this true? Well, rep dd of t here refers to the matrix T hat. So this rep corresponds to this arrow, the matrix that gives me the transformation represented by this arrow. Now the point of arrow diagrams is that you can get from one place to another by any set of arrows. I can go directly, or I can go round Robin Hood's barn this way. So let's go round Robin Hood's barn. The first step is to go from V with respect to D back to V with respect to B. All right. Now notice that I'm going in the opposite direction of this arrow, of this identity map. So in other words, I'm taking the inverse of this mapping. Now this mapping is represented exactly by this term here. Notice that this first mapping that I'm going along is the mapping that's farthest to the right, because we know when we act on vectors, you act on vectors to the left. If I put a vector here, I'll act on this I'll act using this matrix first, and then at the next step I'll act with the next matrix, and then with the next step I'll act with the next matrix. So if I'm trying to trace the action of these three arrows, the first action is here. It's the inverse of this identity map, which is represented by this. So this is the first application I make of a mapping to the vectors in here. Followed by that, I want to map from this representation of V to the representation of T, of the image under T of vectors in V. Right? This arrow is represented by this representation. I'm going from basis B to basis B according to the linear map T. And as we mentioned, that corresponds to this matrix T. Then finally, I want to go from this representation of the image vectors back to the D representation of the image vectors. So I'm changing from basis B to basis D. That corresponds to this term here. So the upshot is that going from here to here directly by application of this matrix is equivalent to going application of three matrices. Each one of these three matrices represents one of these stages. This one represents this one represents this step, and this one represents this step here. Okay. All right, now let's make some definitions that accords with this situation. So here's a repeat of the same diagram, right? Two bases, B and D, same vector space, and linear transformation with respect to B and with respect to D. Okay? So we say that two matrices T and T hat are similar if there's a non-singular P such that T hat equals P, T, P inverse. Now if you look back here, this is just what we have. We have rep BD inverse over here, and here we have rep BD of identity. So the matrix here is the inverse of the matrix here, and vice versa. This corresponds to T. This corresponds to T hat. So if we let this matrix here be P, we have exactly this situation. Okay? So in general, two similar matrices correspond to two representations of the same linear transformation, one with respect to one basis in domain and range, and the other with respect to another basis for domain and range. And P is the change of basis matrix between these two bases. All right, so let's do a practical example. Consider the derivative map. We're familiar with this. Let's consider first the standard basis of polynomials, of degree 2 polynomials. And here's an alternative basis. It's pretty clear that this is a basis. We've seen arguments like that before. Okay. So let's compute this diagram and transmit between the two bases. Okay, so we have T between the standard basis and T represented in this alternative basis. And we're going to show that everything is consistent. All the change of bases matrices work out according to the computations that we just described. Okay, so first of all, let's consider the matrix associated with ddx in terms of the basis B. Okay, so if we take ddx on the three basis vectors, on the basis vector 1 it gives 0, on the basis vector x it gives 1, on the basis vector x squared it gives 2x. And we know that the representation of 0 is 0, 0, 0. The representation of 1 is 1, 0, 0. The representation of 2x is 0, 2, 0. So we get these three relations. Okay? And that's going to give us our matrix capital T. The matrix T is the matrix whose columns are the representations of the images of the basis vectors. That's what we did here. We took the basis vectors. We found their images. We represented the images in terms of the same basis, and these columns are exactly the column vectors of the matrix T. All right, now let's see if we can make this work out with T hat. Remember our expression here that we're going to have to sandwich this with the representation BD of the identity inverse and the representation BD of the identity. So we need to find this matrix representation BD of the identity. So this is how we're going to continue. All right, so we want the representation with respect to this second basis D of the first basis vector in the first basis. And if you remember what D is, I think D is equal to, I believe it's equal to 1 plus x, 1 plus x squared. Okay. So we want to represent the basis vectors in B. Remember, B is the standard basis, 1x squared. We want to represent each of these basis vectors using the basis vectors here. First basis vector here is 1, and 1 is represented by the first basis vector in D, so that's why we have 1, 0, 0. The polynomial 1 is equal to 1 times this plus 0 times this plus 0 times this. The polynomial here, the polynomial x, can be expressed as 1 times this. Sorry, I missed my, let me get this back again. 1 times 1 plus x minus 1. So it's minus 1 times D1 plus 1 times D2 plus 0 times D3. So that's where we get the minus 1, 1, and 0. And similarly for x squared, we can see that the polynomial x squared is equal to this third polynomial minus the second polynomial. So we have a minus 1 in the second place and a 1 in the third place. Okay, so we have the representation with respect to D of the images of all the basis vectors. I'm sorry, we have the representation with respect to D of the basis vectors in B. And by the definition of change of basis vector, change of basis matrix, by definition of change of basis matrix, the columns of the change of basis matrix are simply these columns. Okay. Once you compute that, you can compute P inverse directly by methods we've seen. And then you can construct P, T, P inverse and obtain this result. Okay, so this should be the representation with respect to basis D of the ddx operation, the ddx linear transformation. Okay, so let's check. Okay, let's calculate T hat directly. You should have a hat here. Okay, the effect of the map on the basis elements is, remember, we're looking at the D basis now. ddx of the first element in the D basis is ddx of 1, which gives 0. ddx of the second D basis element is 1. ddx of the third basis element is 1 plus 2x. Now let's represent these results in terms of the D basis. Representation of 0 with respect to the D basis is 0. Representation of 1 with respect to the D basis is 1, 0, 0. And representation of 1 plus 2x, again, I can write this D basis out. The D basis is equal to 1, 1 plus x, and 1 plus x squared. Now 1 plus 2x is equal to 1 plus 1 plus x. I'm sorry, it's equal to minus 1 plus 2 times 1 plus x. So that's where you get this from. You can verify that minus 1 times 1 plus 2 times 1 plus x gives me 1 plus 2x. Okay? Now the representation with respect to D of the linear transformation will be the matrix which has these as columns, 0, 0, 0 first column, 1, 0, 0 second column, minus 1, 2, 0 third column. That's exactly the same matrix that we got this way by another route. So we have shown that this method is in fact consistent. Okay. Now, we've been explaining what this similarity relationship has to do with linear transformations. But you can just consider similarity as an algebraic relationship. You don't need to refer back to the linear transformations. And there are cases where you want to think about similarity and you don't really care about the geometrical or the transformational meaning. So if I have some matrix T and I have any invertible matrix P, I can form a similar matrix a matrix that's similar to T by multiplying on the left by P and on the right by P inverse. All right, the only matrix similar to the zero matrix is itself. Okay, you can prove that, not so difficult. And the only matrix that's similar to the identity is the identity. Those are good exercises. All right, similarity is in fact an equivalence. We showed a similar relationship that for P, H, Q, right? We have H1 equals PHQ. This defined a similarity relation. And you can say in some sense that this is a special case of this type of similarity. Okay. Now, this is what he's saying. The matrix similarity is a special case of matrix equivalence. All right, so if two matrices are similar, then they are matrix equivalent. So matrix equivalent means exactly what I just said, that H1 is equivalent to H2 if H1 is equal to PH2Q, where P and Q are invertible matrices. Okay, so if in fact I choose Q to be a P inverse, then I have that H1 is similar to H2. So that's why similarity is a special case of equivalence. But it's not necessarily true that if two matrices are equivalent, then they're similar. Okay, you can think about that. Okay. So some matrix equivalence classes split into two or more similarity classes. Okay, so if you have this large set represents an equivalence class for matrix equivalence, then these smaller divisions represent equivalence classes for matrix similarity. So that's why he says that the matrix similarity subdivides matrix equivalence classes into smaller equivalence classes. Okay. So naturally we want a standard form to represent the similarity classes. In other words, we want a representative from each one of these similarity classes that characterizes that particular similarity class. And he says some classes, but not all, are represented by a diagonal form. And we're going to talk about that diagonal form now. Diagonalizability, I'll leave that for the next video.